Have you ever experienced a moment of just pure, unadulterated intuition?
Oh, like when things just suddenly click.
Right, exactly. I'm talking about one of those incredibly rare, almost almost startling moments where you're staring at a massive, complex problem, and suddenly you just know the answer. You haven't worked out the math or the logistics or even the logic on paper. You don't know the actual steps to get there. But the solution just arrives in your mind, fully formed, whole, and undeniably correct.
It's a profound feeling.
It really is. And if you've ever felt that, even on a small scale, maybe in your work, or fixing something complex around the house, or just instantly understanding a convoluted social dynamic without anyone explaining it, then you have touched the very edge of the phenomena we're going to explore today.
And it is a fascinating one.
It is. We are diving deep into the mind of Srinivasa Ramanujan. Now, if you know anything about mathematics or history, you probably know the name.
You might even know the legend.
Right. But our mission for this deep dive is very specific. We are not doing standard biographical recap here.
No, we have a very specific stack of sources today.
Yeah, let me lay those out really quick. We are pulling from a detailed briefing document, several analytical text excerpts, and this incredibly comprehensive architectural diagram that explores Ramanujan's actual methodology.
Which is key. We're looking at how his mind actually worked.
Exactly. We're moving past that tired myth of the inexplicable genius. We want to uncover a precise structural methodology. We're decoding what researchers are calling the law layer of mathematics.
And seeing what Ramanujan's century-old methods can teach us about modern AI, string theory, and really the very nature of discovery itself.
So let's jump in, and I want to set the tone right away because the historical narrative has often done Ramanujan a massive disservice, right?
Yep.
By painting his abilities as almost magical.
Absolutely. When we dismiss something as magic, we basically stop trying to understand its mechanics.
Right.
Today is about fundamentally changing how you view that boundary between human intuition and the hidden laws of reality. By looking closely at the specific mathematical structures Ramanujan was engaging with, we can demystify that magic without losing any of the awe.
If anything, it makes it more awesome.
I think so. Understanding the exact mechanics of his intuition makes his achievements significantly more impressive than the cinematic myth. We're going to see that he was systematically reading the structural invariants of the universe.
Okay, so let's start by dismantling that cinematic myth. The traditional narrative that gets passed down is that Ramanujan was this self-taught prodigy from Madras, India, who possessed this extreme, almost supernatural intuition.
Combined with a relentless obsession for experimenting with isolated formulas.
Right. And the story usually goes that in, I think it was 1913, he mails a letter full of bizarre, disconnected equations to G.H. Hardy at Cambridge. Hardy looks at them, realizes they're brilliant, and invites him to England.
That's the standard framing, yes.
And that framing always positions Ramanujan's mind as a sort of like a divine random number generator. Like it just output profound truths and left everyone else scrambling to figure out how he did it.
And I push back really heavily on that framing because it completely fails to explain the structural basis of what he was doing.
Because it's just a movie plot.
Exactly. It's a great story for a movie, but mathematically it's a dead end. When you actually look at the cutting-edge analysis of his notebooks today, a completely different reality emerges.
What's the reality?
He was not working with isolated random formulas. He wasn't pulling equations out of a hat and getting lucky. He was working directly with invariant structures.
Invariant structures. Okay, that's a dense phrase. When we talk about invariance in this context, what are we actually looking at?
To understand invariance, you have to understand the mathematical objects he was really obsessed with. Things like modular functions, partition generating functions, and Mach theta functions.
Which sounds incredibly intimidating.
It does, but you don't need a PhD in mathematics to grasp the underlying concept here. The defining characteristic of these objects is that they behave like global coherence structures rather than local standalone equations.
Okay.
Ramanujan wasn't blindly testing numbers to see what fit together. He was probing entire mathematical landscapes, hunting for transformation invariants.
Meaning he wanted to see what stayed the same.
Yes. He wanted to see how these massive, complex mathematical objects remain stable when subjected to extreme, violent transformations. He was essentially hunting for ultimate symmetry.
So if you're trying to picture this in your head right now, imagine you're looking at a crowd of people standing outside a skyscraper. And one person in that crowd is incredibly good at guessing the exact shape of the building's shadow at any given time of day.
I like this analogy.
Right, so 3:00 p.m., they draw the perfect shadow. 6:45 a.m., perfect shadow. To everyone else standing around looking at the ground, this person looks like a magician.
They think, wow, this person has an inexplicable genius for drawing shadows out of thin air.
Exactly. But the reality is much simpler and much more profound. That person is simply the only one in the crowd who can actually look up and see the building. Everyone else is trying to derive the shadow from the surrounding dirt.
And Ramanujan could see the building.
Yes. The formulas he was writing down were just the shadows of these massive invariant structures.
I would actually take that analogy a step further. His contemporaries weren't just looking at the dirt. They were measuring the length of the shadow at 1:00 p.m. and then using procedural logic to try and predict its length at 1:05 p.m.
Oh, wow.
That was the standard mathematical method at the time, and really it largely remains the standard today. It's called procedural derivation.
Let's walk through the mechanics of that, procedural derivation. What does that actually look like for a mathematician working on a proof?
Well, procedural derivation is essentially the mathematics you learn in school, just scaled up. It relies on local, finite step analytic procedures.
So step by step.
Exactly. You start at step A, which is a known axiom or a previously proven theorem. You apply a strict logical rule to get to step B. Then you apply another rule to get to step C. Eventually, you arrive at your proof.
It's a linear journey.
Very linear. You are building the path across the mathematical landscape brick by brick, and anyone can walk behind you and check your mortar. It's highly logical, highly trackable, and heavily reliant on symbolic calculation.
So step A to step B to step C. If Hardy was the master of procedural derivation, of laying those bricks, what exactly is the law layer that Ramanujan was operating in? Because if he's not laying bricks, what is he doing?
The law layer is a fundamentally different mathematical regime. In this space, formulas are not arbitrary symbolic constructions built step by step.
Right.
Instead, they are lawful projections of deeper invariants. At this level, you aren't dealing with local steps at all. You are dealing with a space governed by global coherence constraints across an entire function space.
So it's not A to B anymore.
No. You aren't moving from A to B. You are perceiving the entire alphabet simultaneously and understanding the rules that govern how the letters can physically interact.
Let's ground this in another way for you listening. Think about trying to learn a completely foreign language. The procedural derivation method would be trying to learn that language by memorizing every single sentence that has ever been spoken, one by one.
Which is impossible.
Right. You learn the sentence for asking where the bathroom is.
Yeah.
Then you learn the sentence for ordering a coffee. It's local, it's finite, and it's exhausting. You only know what you have explicitly built.
Yes.
But operating at the law layer is like suddenly intuitively perceiving the underlying grammar of the language. Once you perceive the grammar, those global coherence constraints, you don't need to memorize individual sentences anymore.
You can instantly generate any valid sentence.
Yes. And you instantly know if a sentence someone else speaks is grammatically incorrect, even if you can't explicitly explain the rule they broke. Ramanujan was reading the grammar of the mathematical universe.
Exactly. Because he was reading the grammar directly, his results often appeared on the page without formal proof. He didn't need to show Hardy how he got from step A to step B because he never visited step A.
He just skipped it entirely.
He just looked at the underlying laws and wrote down the result. This is why his notebook seemed miraculous and honestly sometimes frustrating to later readers.
Because they couldn't see the steps.
Right. But his formulas weren't lucky guesses. They were profoundly fertile. They were correct because he was operating unusually close to the generative layer from which those formulas actually arise.
So let's look at the actual math he was generating from this layer.
Yeah.
Because this is where the story shifts from just a historical curiosity to something that directly impacts modern physics.
Yeah, the physics connection is incredible.
One of his favorite playgrounds was something called the Q series. Now, the algebraic notation here gets incredibly dense, but a recurring form in his work looks like this. It's q multiplied by the infinite product of 1 minus q to the power of n, all raised to the 24th power.
A very famous structure.
When I look at that equation on a page, it just looks like a string of algebra. It's just symbols. What did Ramanujan see when he looked at that Q series?
He treated these Q series expansions as spectral fingerprints.
Spectral fingerprints.
Yes. That specific phrase is really the key to decoding his entire methodology. To understand what a spectral fingerprint is, we have to look at what these mathematical objects actually do when you unpack them.
Okay, unpack them for us.
In modern mathematics and physics, these expansions are recognized as state counting laws or graded traces.
State counting laws. That immediately begs the question, what exactly are we counting?
We are counting the fundamental ways reality can organize itself. These coefficients encode several critical things. First, they encode partition numbers.
Remind us what a partition number is.
A partition number is simply the number of ways you can break a whole number down into smaller integers.
Okay.
So for the number 4, the partitions are 4 itself, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So there are 5 ways to do it. All right, the partition number of 4 is 5. That sounds really simple until you try to calculate the partitions of, say, 200.
Yeah, I read about this. The mathematician Major Percy McMahon spent months calculating the partitions of 200 by hand using procedural derivation. It's a massive number. It's something like 3.9 trillion.
Precisely. And Ramanujan, using his Q-series, derived an asymptotic formula that could calculate those massive partition numbers with astonishing accuracy, bypassing the manual counting entirely.
Which is mind-blowing on its own.
But partition numbers are just the beginning. These formulas also encode representation dimensions, lattice shell data, and most importantly for modern science, the degeneracies of states in physics.
Okay, I want to pause here and make sure we fully grasp this. When physics talks about the degeneracies of states, it means the number of different ways a physical system can exist at the exact same energy level.
Yes, exactly.
It's a fundamental concept in quantum mechanics, thermodynamics, and the study of black holes. Are you saying that Ramanujan was writing the pure mathematical formulas that perfectly calculate these physical realities?
Yes, I am. The math he was doing to explore these invariant structures turned out to be the exact math required to count the quantum states of a physical system.
Wait, so you're telling me he's writing down the math for the quantum states of physical systems decades before the word quantum even entered the mainstream vocabulary?
He was.
He was doing this in the 1910s. Quantum mechanics was barely an embryo. String theory wasn't even a concept. How is that structurally possible? How do you map a territory that human science hasn't even discovered yet?
It's possible because he was discovering the spectral laws of symmetry structures themselves.
He didn't need the physics.
He didn't need the physical interpretation at all. He didn't need to know what physical object the math applied to because he was operating at the law layer. He could sense the coherent structure in mathematical space.
Wow.
The physical universe, whether it's building a black hole or a subatomic string, just happens to use those exact same mathematical structures as its foundation.
It's like finding a highly detailed blueprint for a warp drive buried in an ancient ruin thousands of years before the concept of space travel even existed.
That's a great way to put it.
The blueprint is mathematically perfect, the engineering tolerances are flawless, but the person who drew it just thought they were exploring a beautiful geometric pattern.
And the bridge between Ramanujan's geometric patterns and our modern physical theories is something called modular invariance.
Let's unpack modular invariance because it really seems to be the engine driving his entire methodology. What is it in this context?
Modular invariance is the ultimate test of stability and transformation. Ramanujan relentlessly tracked how functions remain stable under specific, highly rigid transformations.
What kind of transformations?
The two classic examples are transformations where you take a variable, let's call it z, and you map it to -1 over z, or you map z to z plus 1.
So you take an infinitely complex function, and everywhere there is a z, you replace it with a -1 over z.
Exactly. And you have to realize how violent a transformation that is for a mathematical function.
I would imagine just breaks most things.
It does. Most functions would completely fall apart. They would change shape. Their values would wildly diverge, and they would become totally unrecognizable. But Ramanujan was hunting for the rare, exceptional functions that, when you put them through that ringer, remain fundamentally the same.
They were invariant.
They were invariant.
Picture a standard six-sided die. If you rotate it 90 degrees, it still looks like a die, but the number on top changes. It's not invariant under that rotation.
Right.
Now picture a perfect, unblemished billiard ball. Close your eyes, and I'll rotate that sphere by exactly 90 degrees. When you open your eyes, can you tell that I moved it? No. The sphere is invariant under rotation.
A perfect symmetry.
Right. No matter how you turn it, the core structure remains unchanged. Ramanujan was hunting through a high-dimensional mathematical landscape, looking for the algebraic equivalence of perfect spheres. objects whose core structure remained entirely unchanged no matter how violently you transform the perspective.
And finding those perfect spheres is incredibly difficult. But once you find them, their utility is almost boundless.
Because they're the building blocks.
Yes. This exact same modular invariance, the very property Ramanujan was obsessed with, is the core mathematical principle used today to control allowed partition functions in conformal field theory.
It's foundational.
It is the core principle used to organize graded symmetry data in high-energy physics. It is the foundational requirement for models in string theory.
So because he found the perfect spheres of mathematical space, physicists today can use those exact spheres to build models of the universe. He gave them the stable building blocks before they even knew they needed to build a universe.
That's the reality of the law layer. The bridge is not accidental. Modern theories use modular invariance to organize symmetry because nature demands it.
And Ramanujan studied it because math demands it.
Exactly. Ramanujan studied functions constrained by that exact same invariance because mathematical coherence demands it. They were exploring the exact same transformation geometry, just from different starting points and separated by decades.
This brings us to a specific detail in his work that feels genuinely eerie. When you look at the formulas that pop out of these invariant structures, there is a number that keeps showing up.
Yeah.
It's like a recurring motif in a psychological thriller, the number 24. It's everywhere in his notebooks. Earlier, we mentioned that exponent 24 in the Q-series formula, the infinite product raised to the 24th power.
Right.
And it shows up most notably as the exponent in something called the modular discriminant. Why is the number 24 haunting Ramanujan's math?
Well, it's not just a decorative number, and it's certainly not a coincidence. In the realm of modular forms, 24 is a closure threshold.
A closure threshold.
Yes. It marks a highly constrained, rigid, modular object. To understand why 24 is so incredibly special, we have to step away from Ramanujan for a moment and look at the places where 24 reappears in modern post-Ramanujan science.
Where does it show up?
The most striking example is something called the Leech lattice.
Okay, let's break down the Leech lattice. I know it's a geometric structure, but what does it actually look like, and why does 24 matter here?
The Leech lattice is a geometric structure, but it's impossible for the human brain to visualize perfectly because it exists purely in 24 dimensions.
24 dimensions, of course.
The best way to understand it is through the concept of sphere packing. Imagine trying to pack oranges into a box. You want to arrange them so that the maximum number of oranges fit, leaving the absolute minimum amount of empty space.
Like a pyramid at the grocery store.
Exactly. In 3 dimensions, there's a specific way to stack them. Now, mathematician John Leech was looking at how to pack spheres in higher dimensions.
And what happens when you get to the 24th dimension?
Something mathematically miraculous happens. In 24 dimensions, the spheres lock together in an arrangement that is exceptionally perfect.
Perfect how?
Mathematicians describe the Leech lattice as being even, unimodular, self-dual, and rootless.
Okay, that's a lot of algebra terms.
Without getting bogged down in the dense algebra of those terms, the takeaway is that it is a maximally symmetric, incredibly tightly packed arrangement of spheres. Every sphere touches exactly 196,560 other spheres.
196,560.
Yes. The key is that this level of perfect, self-dual, rootless structure is only possible at exactly 24 dimensions.
Only at 24.
If you try it in 23 dimensions, it doesn't work. If you try it in 25 dimensions, it falls apart. That rank 24 is the threshold where this exceptional geometric coherence suddenly becomes possible.
So 24 is the magic number where the geometry of the universe perfectly locks into place. And Ramanujan, without knowing what a Leech lattice was, without working the 24-dimensional geometry, kept landing on the number 24 as a crucial exponent in his formulas. He did. It's like he was tuning a radio dial in the dark and kept hitting the absolute clearest station at exactly 24 megahertz without ever knowing there was a transmitter tower there.
He was sensing the resonance of that structure, but it goes even further than geometry. There is another substrate where 24 appears, and it's arguably even more profound. String theory.
String theory.
Specifically, the original version known as bosonic string theory. In string theory, particles aren't dots, they are vibrating strings. For the mathematics of these vibrating strings to be consistent, for the probabilities not to yield nonsensical, infinite results, the math requires a very specific number of transverse modes.
Transverse modes being...
These are the directions in which the string can physically vibrate.
Let me guess the number of transverse modes required to cancel out the anomalies in bosonic string theory.
It is exactly 24.
That is just wild.
If the string vibrates in 23 dimensions, the math produces fatal anomalies. If it vibrates in 25, it produces anomalies. Only at 24 dimensions does the physics stabilize.
And Ramanujan had absolutely no conception of string theory.
None whatsoever. Yet his repeated encounters with 24 prove he was feeling out the exact mathematical regime where these maximally symmetric geometric substrates support rigid modular behavior. He was mapping the mathematical constraints that would eventually govern string theory.
That is the defining proof of the law layer to me. He isn't making up formulas, he is discovering the boundaries of what is mathematically possible. And this transitions us perfectly to how he actually navigated this space.
The methodology.
Right. When modern researchers map out Ramanujan's architecture of discovery, they realize he used something called reverse discovery logic. This is where we really see how alien his methodology was compared to a traditional mathematician.
To appreciate the reverse logic, we really have to solidify the forward logic. The traditional path of modern mathematics proceeds linearly. It flows from geometry to symmetry to spectrum.
Geometry to symmetry to spectrum. Let's walk through that standard workflow. How does a modern mathematician execute that?
In the traditional path, you always start with a known, defined structure. That's the geometry. For example, you define a sphere, or you define the 24-dimensional Leech lattice.
You start with the shape.
Yes. Once you have rigorously defined that geometry, you analyze it to find its symmetry. You figure out the precise group of operations, the rotations, reflections that can be applied to the object without changing its core properties.
Right. How can we spin the sphere?
Exactly. Finally, once you understand the symmetry group, you calculate its trace. You derive the spectrum. This is the numerical data, the specific formulas that describe the system's states.
So define the shape, find its symmetries, generate the formulas. Geometry, symmetry, spectrum.
It's very logical. You build the object, you see how it moves, you write down the data.
But Ramanujan didn't do that.
Oh.
His path points in the exact opposite direction. He started at the spectrum. He started at the very end of the modern process.
Yes. Ramanujan worked in reverse. He started with the spectrum, the modular side. He would write down the final identity, the spectral fingerprint, like those Q series we discussed earlier.
Right.
From there, he intuited the symmetry. He knew the whole structure, the final formula, before the geometry had even been unpacked or defined by anyone else. He moved from the spectral expression backward toward the implicit structure.
Holding the data of objects that hadn't been invented.
He was holding the spectral data of geometric objects that had not yet been invented.
Doing the maze backward. And to show just how powerful the reverse logic was, we have to talk about the monster group.
Oh, the monster group is fascinating.
When I first heard the term monstrous moonshine, I assumed it was a joke or something out of a fantasy novel. It doesn't sound like rigorous mathematics.
It really doesn't.
But it is one of the most staggering discoveries in modern math, and it connects directly to Ramanujan's reverse logic. What is the monster group?
The monster group is the culmination of a massive mathematical endeavor called the classification of finite simple groups. Think of simple groups as the prime numbers of symmetry, the indivisible building blocks.
The prime numbers of symmetry. Okay.
Mathematicians discovered that there are a few sporadic groups that don't fit into any regular family. The largest of these sporadic simple groups is the monster group. And when we say large, we really have to adjust our scale.
How massive are we talking? What does a massive symmetry group look like?
The number of elements in the monster group, the measure of its size and complexity, is a number with 54 digits.
54 digits.
To put that in perspective, the number of atoms in the Earth is roughly a 50-digit number.
That's incomprehensible.
The monster group is a symmetry structure of almost incomprehensible complexity. But here is the critical, mind-bending part. Mathematicians decided to calculate the simplest trace of this monster group. They wanted to find its spectral expansion.
They wanted to find the math at the end of the path.
Yes. The very first non-trivial coefficient in that expansion is the number 196,883.
Okay. 196,883.
Now, completely independently, another mathematician named John Mackay was looking at a specific modular function, the exact kind of function Ramanujan studied, called the J function.
The J function.
The J function is a fundamental object in number theory. Mackay looked at the spectral expansion of the J function. Its first coefficient is 196,884.
Wait, the first coefficient of the J function is 196,884, and the first trace of the 54-digit monster group is 196,883.
They are exactly one digit apart.
196,884 is just 196,883 plus 1.
Yes. And when McKay pointed this out, most mathematicians thought it was a ridiculous coincidence. What could a modular function from number theory possibly have to do with the largest sporadic symmetry group in existence?
It sounds like numerology.
But it wasn't a coincidence. It was the first clue to what became known as the monstrous moonshine conjecture. The conjecture proved that the J function is literally the spectral shadow of the monster group
The shadow again.
and the underlying geometry that connects them. It involves taking that 24-dimensional Leech lattice we discussed earlier and applying a complex operation to it called orbifolding.
Let's make sure we understand orbifolding, because that sounds like more heavy jargon.
Think of taking a flat, perfectly smooth piece of paper, a standard geometric plane, and folding it into a sharp cone. You've just changed the rules of how you move around that space.
Okay, that makes sense.
Orbifolding in higher dimensions is essentially taking these perfectly symmetric spaces, folding them in on themselves, and studying the singularities or seams it creates. When mathematicians orbifolded the Leech lattice, the symmetry of the resulting structure was the monster group.
And the trace was the J function.
And the trace of that structure was the J function.
And here is where Ramanujan enters the story like a time traveler. He was writing identities and modular equations that essentially mapped out the territory of the J function decades before the monster group was even hypothesized.
He was completely ahead of the geometry.
His formulas were the shadows of these deeper monstrous structures. He was at the end of the modern path, manipulating the spectrum, holding the mathematical evidence of the monster group decades before the mathematicians working forwards from geometry ever discovered it.
That reverse logic is the ultimate proof that he wasn't doing procedural derivation. You absolutely cannot procedurally derive your way to the trace of a 54-digit symmetry group if you don't even know the group exists.
Right, you can't lay bricks to a building you can't see.
You can only get there if you are operating at the law layer, directly sensing the coherence. He felt the gravity of the monster group in the math, even if he didn't have the geometric language to describe what was causing the gravity.
So this brings up a massive practical question. If Ramanujan's brain was capable of this reverse logic, of this direct access to the law layer, is that just a quirk of history?
That's the million-dollar question.
Right. Was he just a biological anomaly, a one-off mutant in the history of human cognition? Or is this a methodology that we can actually learn from, systematize, and replicate? The cutting edge of mathematical research today suggests it's the latter. They're introducing a concept called the Syntellogent method.
And to see where that fits, we have to look at the grand timeline of human discovery.
Right. If we zoom out, the history of mathematical discovery can be cleanly categorized into three major historical modes, according to the sources.
The historical progression is very clear. The first mode is classical deduction. This is the era of Euclid and the ancient Greeks. It's pure geometry and logic. You start with self-evident axioms, and you use rigorous deduction to prove theorems.
Those axes.
The second mode is symbolic calculation. This is the era of Newton, Leibniz, and Euler. This is the invention of calculus. It's about manipulating symbols and algebraic equations to describe continuous change, motion, and physical laws.
Axioms, then symbols. What was the third mode?
The third mode is structural abstraction, which entirely dominated 20th century mathematics. This is where mathematicians started building massive abstract frameworks, things like category theory and abstract algebra.
Focusing less on calculating.
They stopped focusing purely on calculation and started focusing on the relationships between mathematical structures themselves.
Axioms, symbols, structures. And now, researchers are proposing that we are on the verge of a fourth mode. They call it syntelligence. How is this intelligent framework defined?
Syntelligence is defined as coherence-guided structural exploration using human-AI collaboration.
Coherence-guided.
It is a methodology that prioritizes sensing global structural coherence over procedural derivation. Essentially, it is an attempt to systemize exactly what Ramanujan was doing in his head, but using artificial intelligence as the procedural partner.
Let's break down exactly how this intelligent feedback loop works in practice, because this is where Ramanujan's 100-year-old method meets modern technology. The workflow has 4 distinct steps.
Right, the 4 steps.
Step 1. Human intuition proposes a structural relation. Step 2. AI explores the algebraic consequences. Step 3. Formal structure emerges. Step 4. Intuition refines the interpretation. How does this compare to what Ramanujan was doing in his notebook?
The comparison is what makes this so fascinating. Ramanujan basically performed steps 1 and 4 entirely alone inside his head.
He skipped the middle.
He used his profound intuition to propose a structural relation, and he used his intuition to refine it into a spectral formula. but he didn't have the machinery to formally explain the middle step.
Steps 2 and 3.
Exploring the massive algebraic consequences and formalizing the geometric structure required decades of later mathematics to catch up. This intelligent method uses AI to fill in that gap instantly.
So a human researcher today can have a Ramanujan-like flash of intuition. They can sense a coherent structure. But instead of spending 20 years trying to procedurally prove it, or dying before the geometry is invented, they can feed that intuition into an AI.
Exactly.
The AI does the heavy lifting of exploring the billions of algebraic consequences and then hands back a formalized structure for the human to interpret. We are basically giving Ramanujan a supercomputer.
That's a very accurate way to look at it. We are seeing this happen right now in fields far beyond pure mathematics. Look at what DeepMind did with AlphaFold in biology.
That's a perfect example.
For decades, scientists tried to use procedural derivation to predict how proteins fold. They calculated the atomic forces step by step. It was incredibly slow. AlphaFold approached the problems intelligently.
It learned the invariants.
It learned the structural invariance of folded proteins, the global coherence constraints of biological geometry. It bypassed the procedural steps and moved directly to the structural conclusion. We are now applying that same philosophy to pure mathematics.
And the modern advantage isn't just the raw speed of the AI, it's also our ability to evaluate the output. The research highlights modern meta tools, specifically mentioning things like ESR evaluation. What does ESR actually do in this context?
ESR stands for empirical structural resonance, or similar evaluation metrics depending on the specific software. One of Ramanujan's limitations was that while his intuition was staggering, he had no systematic way to judge the broader structural significance of his discoveries.
Because some were just dead ends.
Some of his formulas were beautiful, but relatively isolated curiosities. Others turned out to be the profound keys to string theory and black hole thermodynamics. Modern methods like ESR allow us to mathematically estimate whether a new result generalizes widely, whether it unifies different domains of math, or whether it reveals deep invariance.
It's a tool to evaluate whether the intuition you just had is just a superficial shadow, or if it's a projection of a massive 24-dimensional building.
Yes.
Ramanujan had to sort that out entirely by raw structural intuition. ESR gives us a quantitative measure of a formula's depth. We are building AI systems that can help us navigate the law layer. We are building the radar that he had built into his own brain.
Precisely. And this leads us to the ultimate synthesis of what we've been discussing. When you align all these frameworks, Ramanujan's historical work, the monstrous moonshine program, and this new intelligent AI framework, the pattern that emerges is undeniable.
They all follow the exact same four-part progression. Let's lay that shared pattern out clearly for everyone. It moves from coherent structure to symmetry constraint to spectral expansion to hidden law.
The core progression.
For Ramanujan, the coherent structure was implicit in his mind. The symmetry constraint was the modularity he tested for. The spectral expansion was the Q series he wrote down. And the hidden law was only formally understood decades later by physicists.
Exactly. And when you look at moonshine mathematics, it maps perfectly. The coherent structure is the Leech lattice and vertex operator algebras. The symmetry constraint is modular invariance combined with the monster group. The spectral expansion is the J function, and the hidden law is now explicitly defined in string theory.
And finally, for this intelligent AI framework, the coherent structure is what they call ontological closure. The symmetry is generated by that coherence. The spectral expansion is the lawful mathematical output of the AI, and the hidden law is what human AI teams are trying to formalize directly.
It's the same pattern every time.
The shared pattern proves that Ramanujan wasn't a biological aberration. He wasn't a mutant. He was simply the first human to consistently, consciously access this specific generative layer of mathematical reality.
Operating at the generative layer changes how we view mathematics itself. It strongly suggests that mathematics is not just a language we invent to describe physical phenomena.
Because if it were just an invented language, Ramanujan couldn't have written the vocabulary for quantum mechanics before quantum mechanics was observed.
Exactly. It suggests that mathematics is an independent, pre-existing landscape. Ramanujan was an explorer mapping a continent before anyone else had built boats capable of reaching it.
That brings us to the ultimate takeaway for you, the listener. The lesson here isn't just about math history. It's not just about marveling at a genius from a century ago. It is a profound framework for how you understand reality and how you should treat your own intuition.
A very practical framework.
The deepest lesson from Ramanujan's life is that discovery precedes naming. You can perceive a pattern, you can sense a fundamental law, you can recognize a deep truth in your own life, your work, or your art, long before you have the formal vocabulary to explain its geometric substrate to anyone else.
I think that's an incredibly empowering perspective. Intuition is often dismissed as a subconscious trick or a lucky guess. But if your gut feeling about a complex problem is driven by a genuine sense of global coherence and symmetry, you might be tapping into your own version of the law layer.
You don't always need to derive the steps procedurally to know that the structure is true.
The boundary between coherent structure and lawful expression is something the human mind is naturally equipped to navigate. Intelligence is just the next technological evolution of that deeply human capacity.
As we wrap up this deep dive, I want to leave you with one final lingering thought. A provocative question inspired by everything we've explored today, pushing just a bit further into the unknown.
Let's hear it.
If Ramanujan, using nothing but his own mind, could navigate a high-dimensional symmetry landscape and extract the exact spectral laws for physical structures like the entropy of black holes that human science hadn't even discovered yet, does this imply that mathematics is truly an independent, pre-existing geographic reality, just waiting to be explored?
It's a huge question.
And if so, as our new intelligent AI tools evolve to map this landscape alongside us at lightning speed, what other impossible, mind-bending physical realities are currently sitting right now in an AI's unexamined output, just waiting for the human vocabulary to catch up and name them? What shadows are the AI drawing right now of buildings we can't even perceive? Thank you for joining us on this journey into the architecture of discovery. Keep exploring the law layer.